Hi girls, today we are going to see about eddy currents. Eddy means small concentric circles or they are in the form of ripples. They are called as eddy currents. And according to Faraday's law of electromagnetic induction, an EMF is induced in a conductor when the magnetic flux passing through it changes. That is, when magnetic flux changes, an EMF is induced. That is the main point. This induced EMF is called electromagnetic induction. So main thing is magnetic flux changes. And here when you see this diagram, there is a coil, and around the coil the magnetic lines of force are passing, and this is an AC source. And this AC source produces an eddy currents. The eddy currents, you see, they are in the form of ripples. You see, they are in the form of ripples. These eddy currents, when it is produced in the case of metal plates. And so when you see this, even for a conductor in the form of a sheet or a plate, an EMF is induced when magnetic flux linked with it changes. So usually when you connect an alternating source, this is alternating source, the EMF is, that is, it is alternating in nature. So it will have positive cycle and negative cycle. So the magnetic flux changes, and because of this magnetic flux, and EMF is induced. This is here, and they are in the form of concentric circles. So here what is the eddy currents? All these electric currents resemble eddies of water. So eddies means ripples. They are known as eddy currents, and other name is Foucault currents. So here next we are going to see the demonstration for this. Here there is one simple demonstration for the production of eddy currents. You see this diagram, then you can understand. Here in this diagram, you are having magnetic field north pole and south pole, and between this small pendulum like structure moves. So this pendulum is moving, and when the magnetic field is not, that is when the electromagnet is switched off, that is no magnetism, the pendulum will come to rest due to air friction. That is the main point. Suppose if you switched on this north pole and so electromagnet, then the pendulum will come to rest because of the formation of eddy currents, because eddy current will oppose the motion of the plate. That is the main thing you should know. Here the magnetic field is switched off. So in that case the pendulum will come to rest due to air friction. But here the pendulum will come to rest due to the formation of eddy currents, because the direction of induced current will oppose the motion of the magnet. So this is a demonstration of this experiment. The pendulum now will execute several oscillations before coming to rest. So the pendulum will go here and there, and because of the formation of eddy currents, it comes to rest. But how can you avoid the eddy currents? If some slots are cut in the disc, the eddy currents are reduced. Slots means small holes, or you can say small structures inside the metal. So if you cut some slots in the metal or in the disc, the eddy currents can be reduced. So this is the main thing you should understand. And the drawbacks of eddy currents. So there is the formation of heat that we shall know. The energy loss due to the flow of eddy current is inevitable, but it can be reduced to a greater extent with suitable measures. In some cases, this formation of eddy currents will produce a lot of heat energy, and this heat energy produces some loss in the energy. So here when you see, to avoid this, the core of the transmitter is made up of thin laminas. They are cut into small plates and insulated from one another. And for in the case of electric motor, the winding is made up of a group of wires insulated from one another. You see this diagram, here the plates are laminated. Laminated means they are cut into thin slices and can be used. This core is called laminated core. And here when you see this diagram, this is in the case of electric motor, where the wires are insulated. Insulated means a protected layer is placed on the wire. This insulated wire will avoid the eddy currents. So because of this insulation, the eddy currents are avoided. And in this case, the plate is cut into small slices and it can be used. This is in the case of transformer. So you can avoid eddy currents by these two ways. That is the main thing. Next we shall see about application of eddy currents. There are four main applications: induction stove, eddy current brake, eddy current testing, and electromagnetic damping. And we shall see one by one now, girls. Next we are going to see about induction stove. Here in this induction stove, we are in our houses we are using these induction stoves, and here when you see the eddy currents are formed, and here the cooking vessel is placed on this induction stove and heat is produced, because the formation of eddy currents will result in the formation of heat. So we shall see now about this. Induction stove is used to cook the food quickly and safely with less energy consumption. Induction stoves consume power in a very less manner, so can be used. And here the cooking pan is placed on the induction stove. What happens here is, when the stove is switched off, an alternating current flowing in the coil produces high frequency alternating magnetic field, which induces very strong eddy currents in the cooking pan. So here a strong magnetic field is produced here. Here an alternating frequency is given, AC. This AC will change in direction, so a high alternating magnetic field is produced. This alternating magnetic field will produce eddy currents, which are in the formation of concentric circles like this, and these currents are called as eddy currents. And now the frequency is usually raised from 50 to 60 hertz to 20 to 40 kilohertz. So they are actually in the hertz form, and you increase from hertz to kilohertz, so that a high frequency alternating magnetic field is produced, and this high frequency alternating magnetic field will give more current, eddy currents, and this current will give more heat. So this is a working of cooking stove, or you can call it as induction stove. So the eddy currents have, sometimes it is useful and sometimes it is not useful, but in the case of induction stove it is very useful. That's all, girl. Now we shall see about eddy current brake. So this eddy current brake is mainly used in trains. So the strong electromagnets are fixed above the rails, and these strong electromagnets are switched on to stop the train. That is the main thing. Here there are two cases, linear brake and the next one is circular brake. And we shall see first what about linear brake. This is a diagram for linear brake. That is a plate, and above the plate there is north pole, and eddy currents are produced here. And this is linear brake, and you see this diagram. Here there is a disc, and this disc is rotated along with the wheels of the train, and above and below there is an electromagnet. When the electromagnet is switched off, the eddy currents are produced. These eddy currents will oppose the motion of the disc, and so the train will come to rest immediately after the brake is used. And so here some strong electromagnets are fixed just above the rails, and the electromagnets are switched on. So here, because of this, the magnetic field of these magnet induces eddy currents, which oppose the resist the movement of the train. This is called eddy current linear brake. And in the case of disc, in some cases the circular discs are produced. You see the underlined line, when there is relative motion between the disc and the magnet, the eddy currents are induced in the disc and will stop the train. So this is called eddy current circular brake. Next we shall see about eddy current testing. Testing means in some cases there will be flaws. For example, if we take a gas cylinder, there may be some cracks or air bubbles, and this will cause danger to the when it is used. And so here, in order to find if any cracks are present there, you can use eddy current testing. And here when you see this diagram, here the coil is there, and around the coil there is magnetic field, and an AC source is connected. If you want to find out any crack or something, you have to keep this setup on a plate where you have to test, and there will be formation of eddy currents. If there is any change in phase or amplitude of the eddy currents, then you can find out that there are some cracks or holes present in the system. and that can be rectified. So you see this, the presence of defects cause the changes in phase and amplitude of the eddy current that can be detected by some other means. So these defects can be identified with the help of eddy current testing. And next we shall see about electromagnetic damping. Damping means after oscillation it should come to rest immediately in galvanometer, and for that is called damping. That is, suppose it shows reading, it should be there, that is a pointer should be in the reading for some time, that is it should not oscillate, it should be in rest on the particular reading, that is called damping. The damping can be done with the help of eddy currents. When you see this diagram, the coil, in between the coil there is a soft iron cylinder is placed, and the north pole and south pole is present, and when the coil moves the eddy currents are produced, and because of that the coil will come to rest immediately after showing the reading. That is called electromagnetic damping. So here when you see, when after the armature is deflected, the relative motion between the soft iron cylinder and the radial magnetic field induces eddy current into the cylinder. So this will make the armature to rest immediately. This is called electromagnetic damping. And next we shall see about self-induction. And what is inductor? Inductor is a device used to store energy in a magnetic field when an electric field current passes through it. That is, capacitor and inductor both are only used for storing the energy, and inductors are otherwise in the form of coils, solenoids and toroids. And when you see this diagram, and this is the coil, this is toroid, that is the bunch like structure, that is called toroid, and this is called solenoid. So these are the three forms of inductor. And now what is self induction, that we are going to see now. Here there is a coil, and this coil is connected with the battery and the rheostat. And suppose when you switch on the circuit, what happens? The current increases. So the increase in current produces an increase in the magnetic flux. Because of this increase in magnetic field, an EMF is produced, and this EMF is called self-EMF, self-induced EMF. This self-induced EMF will oppose the growth of current. That is the main thing. So here an electric current flowing through a coil will set up a magnetic field around it, and so the magnetic flux is linked with the coil itself, and so the flux in the coil changes, and because of this change an EMF is induced. This phenomenon is known as self-induction, and the EMF induced is called self-induced EMF. And hope you understand this diagram. Next we shall see about the equations for self-induction. And here when you take n number of turns and phi b be the flux linkage, you know this flux linkage is directly proportional to I, where I is the current flowing through the coil, and you can replace that by a proportionality constant. So n phi b is equal to Li, where L is equal to n phi b by I, and here you can take L as constant of proportionality, which is called self inductance, not self induction, but it is called self inductance. And so this is the main formula. L is equal to n phi by I. And so here suppose if phi is magnetic flux and n number of turns, I is the current, and suppose if I is equal to 1 ampere, then L is equal to n phi b. So in this way you can define self inductance. So this is one type of definition, and we shall see the other one. So self-inductance is defined as a flux linkage of the coil when 1 ampere current flows through it. What is flux linkage? Flux linkage is nothing but n phi b. So this n phi b is called flux linkage, and suppose if 1 ampere current flows, what is the flux linkage? That is the definition for self-inductance. And if we shall see another form of the formula, and you know this is Faraday's law. E is equal to minus d into n phi by dt. Here n phi b is the flux linkage, but this n phi b is nothing but Li. In the next step you are taking L outside, so L into di by dt. So here you can take L this side. So L is equal to minus E by di by dt. This is another formula for self-induction. And E is a EMF, di by dt is rate of change of current. So you have two forms of equation for self-induction. Suppose if di by dt is 1 ampere per second, then L is equal to minus E. So here the minus sign is because the current is in the opposite direction. So here minus E is produced. Here this is another form of definition. The self-induction of the coil is defined as the opposing EMF induced in the coil when the rate of change of current through the coil is 1 ampere per second. Suppose if this di by dt is equal to 1 ampere per second, L is equal to minus E. So in this way you can define self-induction inductance. This is another form of definition. So an opposing EMF induced in the coil when the rate of change of current through the coil is 1 ampere per second. And next we shall see about unit of inductance.